Okay, so these are the practice problems for your polar bonds notes. We'll begin with this set over here. Determine whether the bonds formed by the pairs of elements are nonpolar, polar, or ionic. Okay, so in order to determine that, we need to look at each element in the compound and compare their electronegativities. And we will use our electronegativity chart here to determine those electronegativity values. Okay, so we've got a hydrogen bonded to a chlorine. A hydrogen has an electronegativity of 2.1, and chlorine has an electronegativity of 3.0. So if we subtract those, 3.0 minus 2.1 equals 0.9. So this bond, has an electronegativity difference of 0.9. So if we use our chart from the notes, we'll see that anywhere from 0.4 to 1.0 is what's called a moderately polar covalent bond. And you'll see actually this is the example they used, a hydrogen bonded to a chlorine with a difference of 0.9. Now, we need to not get hung up too much on whether something is moderately polar or something is very polar. As long as you know it's polar, you're okay. And if you can compare that something is more polar than another thing, then we'll be okay. But we'll get back to that. For now, since this has a 0.9 difference, we can just say this is simply polar. Okay. B, an oxygen bonded to an oxygen. Now, we could look at our electronegativity values here. We see oxygen's 3.5, but anytime you have anything bonded to itself, it doesn't matter what the electronegativities are because they're going to be the same, so something minus itself is always 0. And if you have no difference in electronegativity, and you can see from our chart here, 0 to 0.4, you are considered to be nonpolar. So anything bonded to itself is always going to be a nonpolar bond. On part C, chlorine bonded to an oxygen. So again, we'll look at our electronegativity values. Chlorine is 3.0. Oxygen is 3.5. And if you subtract those, they have a difference of 0.5. Which again, we'll look at our chart. That again falls in this moderately polar covalent area, so we will consider this to be a polar bond. Okay, so something I want to stop and compare for a minute though is the difference between this bond between hydrogen and chlorine and this bond between chlorine and oxygen. They're both polar, but since this HCl bond has a difference in electronegativity of 0.9 and this Cl to an O only has a difference of 0.5, this bond is actually more polar than this one. They're both still polar, but this greater difference in electronegativity makes this bond more polar than this bond. Okay, and last we've got potassium and a bromine. So we'll look at our chart. Potassium is 0.8. Bromine is 2.8. Okay, so it gives us a difference of 2.8 minus 0.8 is a difference of 2.0, which we can look at our chart again, and at the bottom, greater than or equal to 2.0 is considered to be an ionic bond. If you've got a huge difference in electronegativity, you're going to be ionic. And I want you to consider what an ionic bond really is. An ionic bond is the bond between a metal and a nonmetal. So metal, nonmetal, we could have predicted pretty easily this one to have been ionic. Moving on to the next set of questions. Arrange the following bonds by increasing polarity. Okay, in order to do that, we'll have to know the electronegativities of each of these involved. So chlorine is 3.0. Oxygen is 3.5. Chlorine is still 3.0. It's bonded to another chlorine here, 3.0. Chlorine 3.0. And nitrogen also 3.0. Okay, so we know for certain this one is going to be nonpolar because it is something bonded to itself. So they have an electronegativity difference of 0.0. And we know that it's perfectly no difference in electronegativity because they're the same elements. This one, it might look like the electronegativity difference because when you subtract these, it looks like it's going to be 0.0. And technically it is. However, in any bond that is not an element bonded to itself, it is going to be somewhat polar. Now, I don't want you to be too confused here, because this chart over here, where 0 to 0.4 difference is nonpolar, that's definitely true. But if something has an electronegativity difference of 0.1, it is technically still a little polar, but as far as nature is concerned or properties are concerned, it's nonpolar. So even though this has an electronegativity difference that appears to be 0.0, since they're not the exact same elements, this is going to be at least somewhat polar, at least more so than this one. And then we've got chlorine and oxygen here. We'll just simply subtract their values, and we have a 0.5 difference in electronegativity. So to answer the question, arrange the following bonds by increasing polarity. That means from least polar to most polar. Well, we know this one, something bonded to itself, is perfectly nonpolar, so that will be our least polar. This Cl to the nitrogen bond looks like it's nonpolar, but it is going to be at least more polar than a chlorine-chlorine. And then without a doubt, the chlorine-oxygen bond has the greatest difference in electronegativity, so it would be the most polar. So from least polar to most polar. Okay, the next set of questions involves drawing a dipole on the bonds if there is one. Okay, so we will look at these. We've got chlorine bonded to a fluorine. So again, we'll need to know their electronegativity values. Fluorine is 4.0, it's the most electronegative. Chlorine is 3.0. So since fluorine is more electronegative than chlorine, and we'll subtract to prove that it is polar, 4.0 minus 3.0 is 1.0. And a difference of 1 means you're polar. Then this will have a dipole on it because it's a polar molecule. So the dipole always points towards the more electronegative element. It always points to the negative end of the molecule or of the bond. So since fluorine is more electronegative, we'll have a dipole pointing towards the fluorine, and we'll put a little plus on this side showing that the chlorine end of this bond is positive and the fluorine end of this bond is negative. Down here, number 2, we have a bromine bonded to a bromine. Now, I don't even care what bromine's electronegativity is. Because it's bonded to itself, this is going to be nonpolar. It will not have a dipole. Okay, number 3, a carbon bonded to a hydrogen. So we'll look at our electronegativity values. Carbon is 2.5, hydrogen is 2.1. So we'll subtract to find our difference. 2.5 minus 2.1 is a difference of 0.4. And according to our chart, if it's 0.4, that is going to be considered nonpolar. So even though there is a difference in electronegativity, it's not enough to make this molecule or this bond have a dipole. It'll be nonpolar as well. And number 4, fluorine bonded to a hydrogen. We'd set up here that fluorine has an electronegativity of 4.0. And we set up here that hydrogen has an electronegativity of 2.1. So if we subtract those, that's a difference of 1.9. This is going to be quite polar. 1.9, almost as polar as it can get without being ionic. And the dipole is going to point towards the more electronegative element, which in this case is fluorine. So the dipole will point towards fluorine, give it a plus on this side, showing the hydrogen in this bond will be slightly positive, and the fluorine in this bond will be slightly negative.